Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we have completed the questions of GATE 1994 section A. So today we will solve section B and I will upload the section B in two parts because due to some work and spirit is going on in the IIT Guwahati at annual sports fest. So I was engaged with those activities. So but hopefully I will try to upload as soon as possible. I'm trying my best. Okay, so uh, without wasting time, we'll look into the question. So what question is saying? The very first question of section B. From there, we'll start the big questions, the subjective types. Okay, so in a batch reactor, an irreversible first order liquid phase reaction. Very first thing, first order liquid phase. So we have to put expansion factor equal to 0. We know that expansion factor is equal to conversion at sorry uh, volume expansion at full conversion, volume expansion at zero conversion divided by volume expansion at zero conversion. Okay, so this is expansion, but for liquid phase reaction it is zero. Okay, A that gives R takes place. Okay, the rate constant is this first order reaction. The initial concentration of A is this. Okay, this is C A naught. A will come down. Meter cube. Cube will go up. Okay. Find the conversion of the reactor after 2 seconds. Okay. And the reactor is batch reactor. Okay. Batch reactor. So solution conversion of the reactant after 2 seconds. Applying performance equation of the batch reactor. So this is the performance equation for batch reactor when EA equal to 0. Okay. Basically, we will see later. There is a question when EA is not equal to 0. Okay, in this particular video. Okay, we will see that later. Okay, so T is equal to CA naught 0 to XA dXA minus RA. This is the performance equation of a batch reactor. Okay, so for irreversible first order reaction, rate we can written as like this. T is equal to CA naught 0 से XA dXA KCA. Just put the value of minus RA in here. Okay. Then CA is CA naught 1 minus XA. Then T CA naught K CA naught will cancel out. 1 by K will come out. Okay. Into this whole term. Sorry. This is bracket here. Okay. Okay. Like this. So this is the sign of multiplication. Okay. So we'll get, we have put it all the values. Okay. So 2 seconds, 0.2 second inverse value of K. Okay. So second will go up, second inverse will go up and become second. Multiplication minus XA is 0.329. So this is the final answer. Straightforward question. Okay, straightforward. So next question. Saturated steam at 130 degrees Celsius is flowing through a steel pipe of 0.021 meter inside diameter. That is diameter, and 0.027 meter outside diameter. Pipe is insulated outside with 0.38 meter thick insulation. Ambient air outside the insulation is 27 degrees Celsius. That means atmosphere is at 27 degrees Celsius, and heat is taking place from inside steel pipe because the steam is flowing at 130 degrees Celsius to outer side because it is 27 degrees Celsius, and within the outer surface of the pipe is covered with the 0.38 meter thick of insulation. That is very straightforward question. Calculate the rate of heat loss per meter length of the tube. Okay, per meter length, and the overall heat transfer coefficient based on inside surface area of the steel pipe. Okay, based on inside surface. We will calculate for inside as well and for outside as well. Okay. So additional data we have given: thermal conductivity of steel and insulation. This is meter square. Okay. So inside and outside conductivity transfer coefficient. Okay. Okay. So very first we will see the diagram. See, this is our pipe. These two are, this is inside diameter of the pipe. This is inside diameter of the pipe. That is 0.0105, that is radius. If you will into 2, then it becomes 0.021. Okay, so this is radius. Then the outer radius, this is the outer radius of the same steel pipe, that is 0.0135, that is the half of the 0.027, and adding to this value 0.38, that is the insulation. This is the insulation, only this. Okay, sorry, this is the insulation, so you'll get this value. Okay, so this is our R1, this is our R2, and this is our R3. Okay, inside diameter is 130 degrees Celsius, outside diameter is 27 degrees Celsius. When there is a question of composite cylinder, you have to make this kind of diagram. Okay, this will make your question much more easier, and you will stand very in a very easy way. Okay, so very first thing, we know that Q is equal to EA del T M. That is the straightforward question, where U is the overall heat transfer coefficient. If there is like in a composite cylinder, okay, we will see. Then where UI is this, UI is this. Okay, write this formula. It is in RK Rajput heat exchanger. Okay, there is heat exchanger, there is a part, you will find this formula. Okay, so this is for UI, inner heat transfer coefficient. For outer, if you want to write for outer, just replace this Ri with R0. Okay, the same formula will come. Okay, just replace this Ri with R0, that formula becomes for U0. Okay, so next, putting all the values, we have all the values for UI. Okay, just okay, so we have Ri, Hi is inside, Ri ln R2 by R1, R2 R1 45 steel, that is Ka, and this is Kb. Okay, so R3 by R2, R3 R2, and this is the insulation, have the thermoconductivity of 0.064 upon 1 upon H0 R0, outside inside. Okay, so this will give the value of UI will be this. Okay, UI will be this. If you will replace with Ri, as I told you earlier, Ri to R0 for U0, you will get the value of U0 as this. Okay, so we have to calculate based on inside, so this is our answer. Okay, now Q is equal to UI 2 pi R0 L. Since we will use UI because the question is saying that based on UI, but here R0 will use because when the heat will loss from the surrounding, it will go over the outer radius. It will go over the outer radius, then it will transfer outside, right? So answer will be 15.7 watt per meter. Okay, so this is the final answer. Okay, that is also a straightforward question, nothing tricky or something else. Okay, so we'll move to the next question. The heat of reaction at 300 Kelvin at 1 atmospheric pressure of the following gas phase reaction 3A plus 3B, that gives C, is itna. That is the heat of the reaction. Calories per mole. It is in calorie. You know that 1 calorie is equal to 4. Okay, read this. Calories per mole of a converted. Data on the molar heat capacity at constant pressure. Calories per mole. So we need not to change the units because it is in calorie per mole. Heat capacity is calorie per mole. Okay, so there is no need to change the unit. But if there is heat capacity in kilojoule per mole or joule per mole and it is in calorie per mole, then we have to change the units in calorie to mole or calorie to joule or joule to calorie. Okay, of various components are Ca. So it is the function of time. Cp of A is a function of time. Okay, so we need to integrate this somehow. CpCc. Calculate the heat released. Okay, so we have to find the heat released from the reaction at 500 Kelvin at 1 atmosphere pressure. Okay, so very first thing, calculate the heat released from the reaction at 500 Kelvin. We have this equation. I told you earlier in the previous lectures, whenever stoichiometry comes with the heat energy balance, this reaction will come. Okay, stoichiometry comes with the energy balance, this reaction will come. Just uh, inbuilt that in your mind. Okay, so this is the summation of heat of the products, heat of the reactant, heat of the reactant, and heat of the reaction, which is minus 50,000. Okay, so very first thing, if reactant is at 298 Kelvin or 25 degrees Celsius, this automatically becomes zero, but here they are not. Okay, so we'll solve one by one, calculating the heats between 300 to 500 Kelvin. Very first, we have calculated for products NCP delta T. We have product only C. Okay, so NCP delta T 300 to 500, 26 dt, that is 26, that is, so 26 into del T will come. So this is the product heat. Now calculating for reactant, and we have two reactant A and B. So NCP delta T 300 to 500, CP delta T, that is NCP delta T, that is totally fine. So 1 mole of A, and it is a function of time, 300 to 500, then 3 mole of B, and it is straightforward 7, not function of time. This will give this. Okay, now see, we have multiplied moles and specific heat, calorie per mole and Kelvin. So mole will cancel out, and Kelvin will cancel out. So only calorie will be remains. Okay, now here calorie only, here calorie only, but delta H reaction is in calorie per mole. So we have to multiply with the conversion. How much A is converted? Okay, how much A is converted? And A is converting 1. That is complete. Because there is no A in the product. So mole will come. 1 mole. Mole cancel. Okay, now we can put the value. So this is the answer. Okay. So going to the next question. Air at 300 degrees Celsius and 150 kilopascal in a closed container is compressed and cooled at 300 degrees Celsius and 150 kilopascal in a closed container. After that, it is compressed, and it is found that the first droplet of the water condenses at 200 kilopascal 50 degrees Celsius. Calculate the percentage humidity of the original layer. So we have to calculate the percentage humidity at this condition. Okay, at this condition, percentage humidity, percentage relative humidity. If percentage humidity will come, then the formula will change. The vapor pressure of water at 15 and 30 degrees Celsius, this and this. So vapor pressure at 15 degrees Celsius and 30 degrees Celsius. But at 15 degrees Celsius, vapor pressure, there will be a liquid as well. Okay, so So very first thing, at 30 degrees Celsius and 150 kilopascal, the air is in vapor form. Like there is a air plus water vapor mixture. Water vapor. When we will compress it to 15 degrees Celsius and 200 kilopascal, there are three things. So what? Air, water vapor, and first drop of liquid, right? But the mole fraction will remain same of water vapor, right? Mole fraction will remain same. Whatever there will be in water vapor, there will be in liquid. Mole fraction will remain same. Okay. Now calculate the percentage humidity of original layer. So very first thing, percentage relative humidity at 30 degrees Celsius and 150 kilopascal we have to calculate, and the formula is partial pressure at this condition, saturation pressure at this condition, and 100. So saturation pressure we have at 30 degrees Celsius 4 point. Okay, we have to calculate the partial pressure. Okay, partial pressure at 30 degrees Celsius and 150 kilopascal we have to calculate. So mole fraction into total pressure, that is the straight formula. So mole fraction will not change. Okay, mole fraction will not change. Moles of the component upon total moles. Moles of the component at 200 kilopascal and 15 degrees Celsius. We can't calculate the mole fraction at this condition. Okay, so we will calculate the mole fraction at this condition, that is moles of the component equal to partial pressure of a component A, that is the PV equal to nRT. Okay, this become total pressure if there is a one component. If there is 2-3 component and we have to find out the moles, then this become partial pressure, right? So mole fraction, what is the mole fraction? Moles of a component upon total moles. So moles of a component at 200 kilopascal and 15 degrees Celsius, PA V upon RT. Okay, that is total moles will be total pressure V upon RT. So put this value here, put these two value here, total moles and moles of the component. We will get PA upon PT, where PA equal to P set because the component is water. Okay, because partial pressure equal to P set. So it will give the mole fraction this. Now this mole fraction we can use here in this equation with the total pressure at 150, and we will find PA. So we will get PA, and this is the answer. So there is a little bit, this question little bit tricky. So hopefully you will understand. If you find any confusion, okay, just comment it below. Now, ethanol can be prepared by the following vapor phase reaction from ethylene. So this is the reaction, and this is vapor phase reaction. The value of del G for the above reaction 1 atm and 125 degrees Celsius it is in joule per mole. Okay. Calculate the conversion obtained if an isothermal reactor operating 125 degrees Celsius and 2 atm is fed with a mixture of 50 mole percent ethylene and 50 mole percent steam. Assume that the equilibrium is reached at the condition of the reactor and gases behaves ideally. Okay. So remember that del G is given at 1 atm and 125 degrees Celsius, and we have to calculate the conversion, that is the extent of the reaction at 125 degrees Celsius and 2 atm. So remember del G is the function of temperature only. Del G is equal to minus RT ln Kp, right? So del G will not change if the pressure will change, but we have to calculate the conversion at 2 atm. So we will see. Now calculate the conversion. Let 1 mole of ethylene, 1 mole of ethylene, 1 mole of ethylene and 1 mole of steam fed to the reactor. Okay. This is the wrong spelling. Okay, just make it correct. Let 1 mole of ethylene and 1 mole of steam fed to the reactor. Okay, so what is the reaction? This is the reaction, and let the extent of the reaction is this. This is the extent of the reaction, that is equivalent to conversion. Now, at t equal to 0, 1 mole, this is 0 mole, right? At t equal to T, this become E. If suppose this has stoichiometric coefficient of 2, then it become 2E. If this has 3, then it become 3E. Okay. Similarly, this is 2E, this is 3E. Similarly, this will become 1 mole fed. How much is reacted? 2E. So, if this has 4, then this become, at 2E, this become 1 minus 4E. And if this is 6, then at 2E, this become 1 minus 6E. Okay. So this is the thing. It will change like that. Okay. Okay. So this is the reaction. At t equal to 0, we have this, no product. At t equal to t, we have extent of reaction 1 minus E, 1 minus E. Okay. Now, we'll solve with pen from here. Because it is difficult to write the formula in presentation. Okay, it takes a lot of time. So now applying the equation. Okay, so we have for this equation Kp is equal to Ky p की power summation of nu, where summation of nu is equal to sum of the stoichiometric coefficient, where the stoichiometric coefficient for product is negative and for reactant is positive. So 1 minus 1 minus 1 minus 1, and the pressure is 2 atm. Okay, so Kp is equal to Ky 2 की power minus 1. Now what is the value of Kp? As I write this, so this is Kp. So we'll del G upon RT minus e की power is equal to, this whole is in e की power is equal to Kp. So this Kp will come, I have calculated. So Kp will come 0.22, 0.22. Okay. So putting all the values, 0.22 is equal to P is 2 minus inverse. Now Ky, what is Ky? So Ky will be very first thing, total moles at equilibrium. So after completing the reaction, what is the summation of moles? 1 minus E plus 1 minus E plus E is equal to 2 minus E. So that is the final moles after the reaction. So what is the mole fraction? So for mole fraction of C2H4 after completion of the reaction, 1 minus E upon 2 minus E, because this remains after the reaction and this is the total moles after the reaction. Y of H2, 1 minus E upon 2 minus E. Okay, now Y of C2H5OH, it will E upon 2 minus E. Now, so this Ky will be E upon 2 minus E upon 1 minus E, 2 minus E into 1 minus E, 2 minus E. Okay, so 0.22 is equal to E upon 2 minus E 1 minus E whole square 2 minus E whole square. This and this one will go into this, become 1 by 2. I will send this 1 by 2 here. Okay. Now when you will calculate this, so 0.44 is equal to E 1 minus E whole square upon sorry, this becomes 2 minus E 2 minus E 1 minus E whole square. This final term will come. Okay. And after solving this, a quadratic equation will come and E is equal to, so for quadratic equation, two values will come. One is 0.167 and other one is 1.83. So 1.83 will not be the value because we have fed 1 mole of ethylene. Okay. So more than 1 is not possible. So this is the answer, 0.167. Okay. So this is also a straightforward question. Now, an experimental determination of vapor liquid equilibrium state of ether 1 and acetone 2. Binary system gave the formula result. Oh, sorry. Binary system gave the following results. X1, so X2 become 0.7, T is equal to 40 degrees Celsius, Y2 0.52, then Y1 become 0.58, if I'm not wrong. Total pressure 10 to power 5 Pascal. Saturation vapor pressure of the pure component at 40 degrees Celsius, or P set we have for both of the components. The vapor pressure can be assumed to be ideal. Okay. Vapor pressure. Okay. That means viscosity coefficient is 1. Calculate the liquid phase activity coefficient. What is the value of excess Gibbs free energy? That is del G upon RT for the liquid phase. Okay. So straightforward questions. If I write for component 1, for component 1, phi y1 pt is equal to x1 gamma 1 p1 set. What is this? Modified Rolle's law. Modified Rolle's law. Okay, Rolle's law. This vapor phase is ideal, so it will become 1. Y1 pt is equal to x1 gamma 1 p1 set. Similarly for component 2, y2 pt x2 gamma 2 p2 set. 1 2. I'll add those two. Okay, so we'll get y1 pt plus y2 pt is equal to x1 gamma 1 p1 set plus x2 gamma 2 p2 set, right? Y1 plus y2, this become pt is equal to x1 gamma 1 p1 set plus x2 gamma 2 p2 set. Okay, this is mole fraction. Summation of mole fraction is always 1. pt is equal to this whole. Okay, so okay, now calculate the liquid phase activity coefficient. Okay, so for liquid phase activity coefficient we have this and this. Okay, so y1 is 0.58, total pressure is 10 to power 5, x1 is 0.3, this we have to find, into 1.21 into 10 to power 5 for component 1, the vapor pressure. Okay, so 10 to power 5 and 10 to power 5 will cancel out. Y1 will become, I have calculated, so actually I have not written the values, so need to calculate it. Calculator, this. So 0.58 divided by 0.3 divided by 1.21, 1.597. So it will give the value of 1.597. Similarly, y2 is equal to 0.42 divided by 0.7 divided by 0.56. 1.071. 1.71428. Okay. So y1, y2 we have calculated. Now del G upon RT. I is equal to 1 से लेके n xi ln yi. Okay. So for two component, x1 ln gamma 1 plus x2 ln gamma 2. Okay. If the question is saying only the value of Gibbs free energy, then you have to multiply with RT. So okay. So you will get x1 is 0.3, ln gamma 1 is 1.597 plus x2 0.7, ln y2 1.071428. Okay, just calculate it. Child's play. Okay. So the following data were obtained on a section of piping through which an incompressible viscous fluid is flowing. Okay. Point 1. Pressure is this. Cross-sectional area is this. Okay. Cross-sectional area is this. Elevation point 2.2. Pressure is this, cross sectional area is this, fluid velocity is this. Okay, fluid velocity we have given here. Okay, after the pump. Other data: density, pump power delivered by the pump efficiency 1 to 2 or 2 to 1. Okay, and this height is 3 meter we have. Okay, so very first thing you will apply the Bernoulli's equation for the real fluid. So this is pressure head, this is velocity head, this is potential head. Okay, this is pump head. Okay, so putting all the values and have to predict whether flow is going to 1 to 2 or 2 to 1. Okay, but we don't have here pump head. We need to find pump head to uh, find out whether the flow is taking place from point 1 to 2 or 2 to 1. Okay, so we have power delivered by the pump, and the power delivered by the pump is given by this formula, rho g q hp. Now putting all the values, hp will come 0.5 meter, putting this value here. Okay, so 15.05 and 15.55. So flow always takes place from higher pressure to lower pressure, higher pressure to lower pressure. So the flow will be 2 to 1. Okay, 2 to 1, because this pressure is high and this pressure is low. Okay. Okay. A tube of 0.05 meter square cross-sectional area is packed with spherical particles up to a height of 0.25 meter. The porosity, there should be full stop. The porosity of the bed is 0.35. It is desired to fluidize a particle with water. Density this and mu is this. Calculate the minimum fluidization velocity given in the Argand equation. Given the Argand equation, minimum fluidization velocity we have to find out. We have given with the Argand equation. Diameter of the particle, density of the solid particle. Okay. So there is no mentioning about the flow is laminar or flow is turbulent. So we need to consider the whole equation. If in the question it is saying that the flow is laminar, then turbulent term becomes 0. If in the question it is saying that the flow is turbulent, then the laminar term becomes 0. But there is no laminar and no turbulent, so we have to consider whole equation. So very first thing, the equation is this. Okay, you can write it. If you will rearrange this equation, it will become this. But I have I have remembered this equation like this, so I will write this equation. Okay, now put all the values, you will get this. So at incipient fluidization or minimum fluidization? At incipient fluidization or minimum fluidization, both are same. Minimum fluidization, this whole term become this. Okay, so after putting all the values, we will get this equation. Okay, and then this is the quadratic equation. Just apply Sridharachar, for that is quadratic formula. So we will get velocity 60 mm per second. Okay. No, this is not thick modulus. This is Thiele modulus. I just copied it from the paper, and there are lot of mistake in the paper. So sorry. Thiele modulus. For a first order isothermal reaction for a flat plate geometry catalyst is found to be 0.2. Calculate the catalyst effectiveness factor. So it is straightforward. Time for first order reaction, it is like this. Okay. This question: 50% conversion is obtained in a CSTR for homogeneous isothermal liquid phase irreversible second order reaction. What is the conversion if the reactor volume is 5 times the original, else remaining same? So very first thing, there is a performance equation of CSTR. Okay, this we will take this and this. So this, sorry. Okay, now 50% conversion is obtained in CSTR. Okay, so V by V naught is equal to CA naught 0.5 minus 0 upon minus RA. So is a second order reaction. So minus Ra is equal to KCa square. Liquid phase reaction Ea is equal to 0. Okay, I'll write it complete. Ca naught 1 minus Xa square 1 plus epsilon A Xa square. So this is equal to 0. So this becomes 0. So this will become K Ca naught square 1 minus Xa square. Okay, so we'll put value K Ca naught square 1 minus Xa is 0.5 square. Okay, so Ca naught 1 C naught will cancel out. So V is equal to, that is V1, V naught upon K Ca naught, and this become 0.5 upon 0.5 square. Okay, so this will become 2V naught upon K Ca naught at first condition. Second condition, the same equation will come, but the volume is 5 times the original volume. So 5V1 upon V naught is equal to Ca naught. And now we have to find the conversion. X1 K Ca naught square 1 minus X1 whole square. Now Ca naught cancel out. 5V1 5. V1 is upon V naught. V1 is 2V naught upon K Ca naught is equal to X1 K Ca naught 1 minus X1 whole square. So K Ca naught V naught, this become 10 1 minus X1 square is equal to X1. So this again become the quadratic equation. Okay, so this again become the quadratic equation. So after solving this, yeah, so this become the quadratic equation. So after solving this, x1 will come equal to 72.98. Okay, percent. Okay, now this question is very important. A homogeneous gas phase decomposition, gas phase. See, this is gas phase. So expansion factor will not be equal to 0. 4A that gives B plus 7S takes place in an isothermal plug flow reactor. The reaction rate is first order, K1 is this, Ca0 is this, feed flow rate is this. Determine the size of the reactor in order to achieve 50% conversion. Okay. So very first thing, performance equation of a plug flow reactor. Right. Now, minus Ra will be this, KCa. Minus Ra will be minus Ra is equal to KCa, and Ca is Ca0 1 minus Xa 1 plus epsilon A Xa. That is the value of Ca. Okay, so I put it the value. Now, rearranging expansion factor. This is the value. Straightforward. 8 minus 4 upon 4 equal to 1. Okay. So, how? Final moles at x equal to 1. Initial mole at x equal to 0. Initial mole. Okay, so will be 1. Okay, now putting the value 1. We have put it this 1. Now, V upon V naught is equal to Ca naught, right, upon K Ca naught. 0 से x से 1 plus x से 1 minus x. So I have told you to remember some of the direct integration, because if you will do this integration in exam, it will almost kill your 15 to 20 minutes. Okay, so remember the direct a result of these integrations so that you will save time in the actual examination. So I have remember this the result of this integration. So we will apply that here. V by V naught is equal to 1 by K become 1 by K because CA naught and CA naught cancel out. Okay. So the value of this integration, remember, minus ln 1 minus XA minus epsilon A XA plus ln 1 minus XA. Okay. Here put epsilon A equal to 1. Okay. So this is the direct integration of which of this direct integration of this. If you will take out KCA naught outside, then this whole integration value is this. Okay, now put EA equal to 1 here. So we will get volume is equal to, when you will solve, 8.863 meter cube. Okay, all the other value you have. Okay. Okay, so if you have any confusion, any kind of doubt in the questions we have solved today, just comment it below, and in the next lecture I will complete 1994, then we will start 1995 as soon as possible, and hopefully I will upload as soon as possible. Okay, so it is just a request. If you want to subscribe or want to share this channel, then please subscribe and share. Okay, take care guys, bye.